Okay, as promised, here's our material for chapter 16. We're only doing, I think, the first 3 sections of chapter 13 due to time, and you can be sure of that by looking at the perusal assignment. That reading is what you're responsible for knowing. So basically in chapter 16 we're talking about planar motion, and this can have a lot of different sort of looks to it. But basically we're thinking of a rigid body. So a rigid body is one that's not going to deform, and sort of the idea is the relative position of separate different particles is always going to be maintained, sort of their relative separation. And then the way that they move is always has to be happening in a plane. So you might have the picture like this amusement park ride. We're also going to look at something a little bit more applied, when we're thinking about gears and, how are they going to be moving and what kinds of things do we need to know about those. So as I said, for a rigid body, we're thinking of something that we can't really treat it as a particle, but, so we have to think about what does it look like, what kind of shape does it have, but again, it's rigid, so it's not going to be changing shape. So, we start off with a simpler case in chapter 16. If we had had more time, we would go on to some, not be limited to planar motion. Basically, here we've defined planar motion if all the parts of the object move in paths that are equidistant from some sort of fixed plane. And we're going to look at a few examples of what it would be. So we actually could talk about like just translation. So in here you kind of see 2 points on the object. They stay parallel to the original direction of motion. So it's sort of like rectilinear motion if they're just moving in sort of one dimension. But we could have a curved path that those 2 objects are taking, and so that would be curvilinear translation. We would also include rotation because of the idea is the particles here, you can see they're moving in little circles, and that circle's in a plane, so that does actually sort of correspond to the definition that we came up with. And finally, we might have a little bit of a combination of the 2. Notice here, it looks like we're sort of have some curvilinear motion, but there's also a little bit of rotation going on. So those are the types of motion that we can be looking at. So the first thing that we're going to start with is sort of translational motion, and sorry about the fact that this doesn't do subscripts. So for instance, we have an object here, and we're going to put a coordinate system that moves with the object and also think about a fixed coordinate system. And so we have 2 points on the object, point A and point B, and notice that we can define point A and point B relative to our fixed coordinate system, and we've also defined where B is in relation to A, which would be within the moving system. And so what we want to think about is, what's going to be true about velocities and accelerations in this type of situation. So we're going to start again. I'm going to rewrite this expression so we remember it. And if we want to define velocity, of course, that's the derivative of r with respect to t. So we would have take the derivative of all 3 of these. And the first term, this is going to give us our velocity of point B. And the second expression would give the velocity of point A. Now this is talking basically about this vector right here that is the motion is sort of B with respect to A. And this derivative then, of course, would be talking about whether it changes or not. But it's a rigid body, so by definition of the fact that it's a rigid body, this quantity is actually 0. And then from this, we could also find the acceleration, of course, is the derivative of velocity with respect to time. And so here we would find the acceleration of B would be equal to the acceleration of A. And so that sort of helps us understand, how would a rigid body be moving in different points on it when we have translational motion. And basically what we found was that all the points on the rigid body for strict translation are going to have the same acceleration and velocity. Just to remind you, this is what we found on the previous slide, which really sort of in an equation way supports what we just stated. So now we want to think about rotation, about some sort of fixed axis. And there's a lot of different things that we want to look at right here. And here is a little font issue. So here's our object, the blue shaded object, and it's rotating about a vertical axis in this location. The way that we're going to talk about the position of a point on the object is that we're going to use the angle theta, so that's our position vector. And we're also going to sort of think about like how are we going to find angular velocity, angular acceleration, etc. So you can see that in this picture the object is moving in this way. It started off here and it's moving along. There's the angle theta. And notice here that because of that motion, we can use the right-hand rule to figure out sort of what would be the direction of, say, omega, and also angular acceleration if it has any. And the way that it works, remember, angular velocity and angular acceleration, the vector for those are going to be along the axis of rotation. That's the only non-ambiguous way to define them. And the way that we do that then is we curl our fingers in the way that it's moving. So we're curling our fingers around, just around like that, this curve that I showed you earlier. And then the way that our thumb points is going to be the direction of, say, the angular velocity vector and the angular acceleration vector. And so for this particular object, the angular velocity and angular acceleration are pointed up. That's the vector direction. We're measuring our displacement in terms of an angle. We're going to call that angle theta. There's also going to be, we can look at changes in theta. And we also want to remind ourselves the relationship between our angle theta and revolutions. So 1 revolution is 2 pi radians if we're measuring, and we usually do. When we're talking about rotation, we measure things with radians. So here we're looking sort of down on the object, like down from above, and we see again the angular displacement. And so the angular velocity, which we call omega, is going to be defined as d theta dt. And that's all should look familiar to you. We've done this before. Angular acceleration is, of course, the derivative of angular velocity with respect to time, or we could write it as the second derivative of theta with respect to time. One of the special situations is if we have a constant angular acceleration. Again, we're having a little bit of font problem, really sorry about that. So if alpha is equal to some constant value, then this is sort of like we had constant acceleration equations for linear motion. So you might remember these, hopefully you do. They look very similar to our linear quantities, but we've just replaced things like velocity with omega, acceleration is replaced by alpha, etc. So the way that we would look at our angular position is initial angular position plus initial angular velocity times time plus 1/2 alpha t squared. omega is equal to omega naught plus alpha t. And then finally, omega squared is equal to omega naught squared plus 2 alpha theta minus theta naught. These are for constant angular acceleration. Please be careful. On the last test, a lot of people chose to use constant acceleration equations in a case where it wasn't constant, so you don't get to use these whenever you want. You can only use these if you have constant angular acceleration. So, you know, if we have our rotating object rotating about an axis, if we looked at a point on the edge of it, of course, not only will it be rotating with an angular velocity, it's also going to have, you know, that point is also going to have a tangential velocity. Now, we're said that the magnitude of that is going to be equal to the angular velocity times the radius. And we're going to kind of look at this right here and say that where does that come from? So if you remember a circle and it has a radius r, and then this piece right here is the arc length that is subtended by the angle theta, we learned that the relationship between these three quantities is s equals r theta. Now, if I wanted to look at the velocity at the edge, that's really ds dt is v, and that would be then dr dt, sorry, theta plus r d theta dt. That's using the product rule for our differentiation. Now, of course, this is 0 because our radius isn't changing. So the velocity is equal to r d theta dt, which is equal to r omega. So that's where that relationship comes from. Sort of upping our game a little bit if we want to talk about more, this is, you know, the magnitude of how big it is. If we think about how do we find that vector just in general, we're going to use the fact that the velocity can be found by taking omega cross r. So it's r sub p. That's those two vectors. So the r is going from, say, some central point to where p is, and then if we cross that with omega, that's going to give us, or omega cross r, sorry about that, that's going to give us our velocity vector. This is actually going to give us both the direction and the magnitude, but you can see that we're going to get omega times r for that expression. Now we also want to talk about acceleration, and we should understand that here you notice we have two different types of acceleration because a point P on that rotating object could have the chance to accelerate tangentially. That's if the velocity, if it's changing its rotation rate. That's going to happen. And then the normal component is basically, due to, that's a radial acceleration or centripetal. So we used V is equal to R omega. Acceleration is going to be caused by a change in the magnitude of the speed of the velocity. So that's going to be R d omega dt, which is equal to R alpha. That's our tangential acceleration. So we know that that's true. Our normal component of acceleration, the radial, is v squared over r. If we substitute in r omega, we're going to get r omega squared is our normal acceleration. Now, it turns out that that's the magnitudes again, but because we're more fancy, we can also take the derivative of velocity with respect to time of the vector, which means we're taking the derivative of omega cross with r. So that's going to give us d omega dt cross r plus omega cross dr dt, and d omega dt is alpha, and now we can do a substitution. Dr dt is just v, and we'll substitute in omega cross r. So these are our two terms. This is our tangential, and this is our normal. And I'm just going to look at that again. So our acceleration we found was alpha cross r plus omega cross r. Now, if you look at this, you can see this is going to have the magnitude of alpha r. Now this one we might want to be convinced with, but if we do the cross products using our right-hand rule, we should notice actually that this result will end up being in the radial direction but inward, and so this will end up being minus omega squared times the r vector. And that's something that you might want to try on your own just to see if you can convince yourself that that's true. Now, the thing that's kind of new for us is this whole idea of like these gears and how do we deal with them. And so what we actually look at is like, so here we have two interlocking gears. They obviously have different radii, and they're both rotating. And so what do we use? What we find is that the tangential, in order for these to be moving smoothly, the tangential velocities and accelerations must be the same. And so, for instance, here we have 2 points. A is on gear B, A prime is on gear C. So if we talk about velocity of A has to be equal to the velocity of A prime, that would be equal to, for velocity of A is going to be the radius of A times its angular velocity. The velocity of A prime is going to be the radius of B times the angular velocity. Sorry, I used the wrong subscript. This is B, sorry, and this one is C. Similarly, the acceleration of point A has to be equal to acceleration of point A prime. So this is going to be RB alpha B, and this is going to be RC alpha C. Now, those, keep in mind, we were talking about tangential velocities and accelerations. Look at these. Notice that these points are also going to have these normal components of acceleration, and those are not going to be the same. The reason, that shouldn't be too surprising, because we found the normal components are omega squared r, and these are different for each wheel and also the radius, and there's no way that we can maintain them being the same. And you can see on the picture that they don't have the same magnitude. So I think what I'm going to do is I'm going to upload this, and then I'm going to have a separate video because I have 2 example problems that I want to do. So here's just the class notes.